All right, we're moving into a chapter in physics called energy. And so in this video, we're going to introduce energy and talk about the different forms of energy, but mostly we're going to focus on how to calculate energy and learn its definition. And so energy is kind of a broad topic. There's a lot of different ways you can define energy, but I like this definition right here because it's very simple. And it says energy is the ability to do work or produce heat. So energy is the ability to do work or produce heat. And in this video, we're going to talk mostly about energy in terms of work and how to calculate it. And so we've introduced in the class this idea of the energy and the law of conservation of energy, which says that energy can't be created, nor can it be destroyed. And so the energy that's here is here. And one thing that's kind of cool about energy is it can be converted from one form to another. And we'll spend a lot of time in class talking about how energy is transferred to different forms and what those different forms are. But in this video, we're really going to focus on how to calculate work, because energy is the ability to do work. And so what exactly is work? Let's talk about its definition. Work is a force acting over a distance. So if we have a force, and you apply a force to something for some distance and you move at a distance, then you have done work on that object. And here's the formula for finding work. Work is equal to a force times a distance. And if you look at those two properties, you'll notice that the units for force, we've talked about units for force throughout the class. The units for force is a Newton. The units for distance is a meter. And so if you're timesing them together, you get a Newton meter. But most physics textbooks will report a Newton meter and all energy units will be given in this unit called a joule. A joule is abbreviated with a capital J. And if you look at how much work or how much energy 1 joule is, here's kind of a way to kind of get an idea or think about how much energy 1 joule is. So if we have a medium-sized apple, and let's say we lifted it in the air for a total distance of 1 meter. And so it will have taken at least 1 Newton of force to lift that apple 1 meter. And so that will have been 1 Newton meter, which is also equal to 1 joule. That will have been 1 joule of energy. So a joule of energy really, as you can see, would not be that much energy. And so a lot of the problems that we're going to talk about throughout the chapter will actually report the energy in terms of kilojoules. So kJ or kilojoules. And that's 1,000 joules because a joule is so small. One thing that I'm really going to emphasize in this video and when we work these problems, when we calculate work, the force, so this force right here, when we calculate work, must be acting in the same direction as its motion in order for it to be considered. So the force must be acting in the same direction as the motion of the object in order to be considered work. Sometimes you'll apply a force and the object moves not exactly in that same direction. And so we'll go over some problems like that and in some of these practice problems. But anyway, I've got 3 practice problems that we're going to work through, and then I'll have your video physics assignment after that. So let's go to practice problem number 1. It says you are pushing a large box across the floor with a force of 100 newtons. If you push it a total of 5 meters, how much work will have been done? Assume you are pushing the box exactly parallel to the direction of its motion. Okay, so let's, as all physics problems, I like to draw a picture to kind of get started. And so here you are, and you're pushing, well, I should draw these, your arms parallel to the ground. And you're pushing this box across the floor with a force of 100 newtons. Okay, and it also said you're going to move it across the floor for a total distance of 5 meters. Now if we go back to the definition or the formula for calculating work, work is equal to a force times a distance. And remember that force has to be parallel, and if you see here, this force is exactly parallel to the direction that the box is moving. And so we can use all 100 newtons here for our force, 100 newtons. Okay, and we're going to times that by the distance that you moved the box, which was 5 meters. And so 100 times 5, you'll see, is 500 Newton meters, or in other words, 500 joules. So you will have done 500 joules worth of work by moving that box for the distance of 5 meters. And that was in this example was pretty easy because the force was exactly parallel to the direction of its motion. Now I've got a couple problems where the force is going to be acting at an angle, and so we're going to have to use our trig functions and remember them to figure out the force that you times the distance by. Okay, let's go through one of them. So this practice problem number 2, it says for this problem you decide to pull the large box instead of push it. So you're going to pull the large box across the floor with a rope that makes a 45-degree angle with the floor. If you still pull with the force of 100 newtons, calculate the amount of work done if you move it 5 meters across the floor. All right, let's draw our picture of what's going on here. So in this time, you're pulling the box with a rope across the floor. And so this rope, it says, makes an angle with the floor of 45 degrees. And so here's that rope. And so here you are. Okay, and you're going to pull it, pull on that rope. And it says here that the rope makes an angle of 45 degrees with the horizontal. And so let's draw in that horizontal here. I'm going to draw in the dotted line. And that's a 45-degree angle right there. And so again, you're going to be moving it for a total distance of 5 meters across the floor. All right, now let's go back to that definition of work, because we're going to be calculating the amount of work that you do here. Work is equal to a force times a distance. But in this problem, we have to pay attention to what direction that force is going in. Remember, it has to be exactly parallel to the direction that this box is moving. The box is moving across the floor, so it's going to be moving straight across the horizontal floor like this. And so when we consider this, this force here that you're pulling on the rope with of 100 newtons, we can't consider this in our calculation of work because this force is not parallel to the direction that this box is moving. So what we're going to do is split up this force into its component parts. And I started doing that with this dotted line here. But let's continue that and continue drawing this triangle up and closing it off. So if this force of 100 Newton, we know that a component of that would be along the x-axis. So I call this Fx, or the force in the x direction because it's on the x-axis. It's going horizontal. This component, the one that's vertical, I'm going to call F sub y, or Fy. Because it's vertical, it's going along the y-axis. And so when we calculate the work, we need this force to be parallel to the direction it's moving. And because it's moving along the floor, we need to find this force, the component of force that's moving in this direction. So we really are looking for here is Fx. Okay, and if you remember, we have a triangle here. It's a right triangle. We have the angle and we have the hypotenuse, but we need to find this side. This side would be called the adjacent side. So if you remember our trig functions, and when we talked about trig, we went over this mnemonic to help us remember the trig functions. It was called SO, CA, TOA. Okay, and this mnemonic helps us remember the trig functions, and here's how we'll use it. We're looking for a trig function that has an adjacent side, because we're looking for Fx, that's the adjacent side. And we know the hypotenuse is 100, so adjacent and hypotenuse in it. if we look here, adjacent and hypotenuse is given here. And so the trig function that we're going to use is cosine. And so here's how you solve that problem. The cosine of 45, because that's our angle, is equal to adjacent, which is fx divided by the hypotenuse, which is 100. Okay. And now we have an equation with just one unknown, so we can solve for it. If we want to get fx by itself, we're going to times both sides of the equation by 100. So 100 times the cosine of 45, and over here the 100s will cancel out. And so fx is equal to 100 times the cosine of 45. And so let me do that on my calculator. 100 times the cosine of 45. And so that looks like the force Fx is going to be equal to 70.7 newtons. And so Fx, F sub x, is equal to 70.7 newtons. And so 70, if we labeled our diagram, 70.7 newtons goes in for Fx. And so when we calculate the work, we can't use all 100 newtons of force that you're pulling on that rope with because it's at an angle. We're looking for the component of that force that is parallel to the motion that the box is moving. And so we're going to use Fx. And so the force that we're going to put in this formula is 70.7 newtons. And we're still pulling it for a total distance of 5 meters. And so we're going to put 5 in there for the distance again. And so if you take 70.7 and times it by 5, I get 353.6. So 353.6. And that will be Newton meters, which is a joule. So you will have done 353.6 joules worth of work by pulling that box across the floor in that kind of configuration. All right, so hopefully that helps you see how if the force is not in already parallel to the direction of its motion, how to find it using trig and plugging that into our work formula to calculate the work done by moving it. I've got one more problem here, and so let's take some time and solve this one. It says, for this problem, you decide to push the large box across the floor. Your arms make a 20-degree angle with the horizon while pushing slightly downward. If you still push with a force of 100 newtons, calculate the amount of work done if you move it 5 meters across the floor. All right, again, as always, let's start by drawing a picture of what's going on here and see if we can make sense of it. So it says that you're pushing the box across the floor with your arms that are slightly at an angle downward. And so here's the box. Okay, and you're pushing slightly downward. It says you make a 20-degree angle with the horizon, or the horizontal. And so if we draw in the horizontal here, and draw in our right triangle, this angle right here would be 20 degrees. It's a little bit small, hopefully you can see that. But it says that you're still pushing with a force of 100 newtons. So the 100 newtons is your hypotenuse of this triangle. Your arms are the hypotenuse. And so you're going to push it again for a total distance across the floor of 5 meters. All right, now it says to calculate the amount of work that you're going to do by moving the box in this configuration. So a good place to start is the formula for work. Work is equal to a force times a distance. And again, the force has to be parallel to the direction that the box is moving. Since the box is moving directly horizontal across the floor, we need the force to also be parallel to that. And so we're looking for this component of the force, which, as we learned, is called Fx because it follows the x-axis. This component of the force over here, Fy, we will not use, but it's Fy because it's along the y-axis. And so let's use our trig, knowledge of trig, to solve for Fx. It looks like, again, we have a adjacent side and we have a hypotenuse. And so if you think of SOHCAHTOA, we're going to use the ka part of that because we have an adjacent and a hypotenuse. So we're going to stick again with cosine. And so let's solve that. Cosine of the angle is 20 this time is equal to adjacent, which is fx, all over the hypotenuse, which would have been 100. Okay, again, we're going to try to get fx by itself. We're going to times each side by 100. On the right side of this equation, the 100s cancel out, and so we're left with the force in the x direction is equal to 100 times the cosine of 20. And so 100 times the cosine of 20, and my calculator is saying 93.969. Let's just call that 94. So the force in the x direction is equal to 94 newtons. And so if we fill in our diagram, this will be 94 newtons. Again, not all 100 newtons of force that you're pushing it with is going to be used to calculate work because this force has to be acting parallel to the direction of its motion. So we've solved for fx. Let's plug it into our equation for work, which is 94 newtons. And we're going to times that by the distance that you moved it. Again, was 5 meters. And 94 times 5 is equal to 470. So 470, and again our units for work or energy in general is going to be joules. So in this configuration you will have used 470 joules worth of energy, worth of work to move that box a total distance of 5 meters. Anyway, hopefully that helps in solving physics problems involving work. I've got now for you your video physics assignment. It's going to be 5 questions that you're going to answer on a separate piece of paper and turn them in for points in the class. I will scroll through them slowly, but remember there's 5 questions, so stick around for all 5 of them. Good luck.